Hello guys, the topic we'll be learning today is called double sideband suppressed carrier, which is written as DSB-SC. But before that, we have to know what is a suppressed carrier system. In a standard amplitude modulated signal, we will have a carrier signal and two sidebands. But only the sidebands will carry the information and the carrier signal will not carry any information at all. It is used only for the transmitting purpose. So this leads to a loss in transmitting power as well as a wasted bandwidth. In order to overcome this disadvantage, we use a suppressed carrier system called DSB-SC. In this system, in this amplitude modulated signal, the carrier is suppressed and only the sidebands are transmitted. This saves transmitting power, but the bandwidth remains same as the amplitude modulated signal. It can be generated, DSB-SC can be generated by the product of carrier and message signal. In this circuit diagram, we can see that the local oscillator generates a carrier signal and both message signal and the carrier signal are passed on to the product modulator where they get multiplied. This gives us the equation Ct into Mt equal to Vc Vm sin omega Ct sin omega Mt. Now we will expand this part using the formula sin A sin B, which is equal to 1 by 2 cos A minus B minus cos A plus B. If we expand it using this formula, we will get the final equation S of t equal to Vc Vm by 2 cos omega c minus omega mt minus cos omega c plus omega mt, which is the expression for DSB-SC. Here I have given the frequency spectrum and phasor representation for the DSB-SC signal. From the frequency spectrum, we can see that the bandwidth is equal to 2 FM, and from the phasor representation, we can see that the resultant is equal to the phasor sum of upper sideband and lower sideband of the AM signal. While talking about the advantages of DSB-SC, we will also have to learn about the efficiency. In a standard AM signal, the total power is equal to the power of carrier plus the power of sidebands, which will give us an expression Pc into 1 plus mu square by 2, where mu is the modulation index. So at 100% modulation and mu is equal to 1, the efficiency will be equal to 33.33%. But in a DSB-SC signal, the total power will be equal to only the power of sidebands. So at 100% modulation and mu equal to 1, the efficiency will be equal to 66.67%, almost twice as the standard AM signal. Now let's learn about the generation of DSB-SC. There are two methods to generate it. One is through the balanced modulator and the other is through the ring modulator. Balanced modulator is commonly used while the ring modulator is most popular. In a balanced modulator, two nonlinear devices are connected in a balanced mode, and the operation is confined only in the nonlinear region. In a ring modulator, four diodes are connected in ring form, and two input and output transformers are used, and a carrier signal is sent through the center taps. This is the circuit diagram for the balanced modulator. A modulating voltage is applied across the two windings of the center tap transformer. These are equal and opposite. Vm is equal to minus Vm prime. The input voltage to transistor T1 is given as VBC is equal to Vc plus Vm. Here the Vm and Vc are in phase. For transistor T2, the input voltage Vm1 plus Vc, Vm and Vc are out of phase. By nonlinearity relationship, the collector current IC and IC1 is written as IC is equal to A1 VBC plus A2 VBC, and IC1 is written as A1 VBC plus A2 V1 BC square. Now, if we substitute the values of VBC and VBC1 in IC and IC1 respectively, we will get the following equations. IC is equal to A1 VC sin omega CT plus Vm sin omega mt plus A2 Vc sin omega CT plus Vm sin omega mt whole square. Now we will expand this using a plus b whole square formula, which is equal to a square plus b square plus 2ab. Similarly, in the IC1, we will have to use the formula a minus b whole square, which is equal to a square plus b square minus 2ab. Using them, we will get the equations IC and IC1. The output of the balanced modulator will be written as K into IC minus IC1 because the collector currents are moving in the opposite directions. So if we substitute the value of IC and IC1 in V0, we will get the output equation as 2KA1 Vm sin omega mt plus 4KA2 Vm Vc sin omega Ct sin omega mt. Next, let us look at the ring modulator. The ring modulator, as I have informed before, has 4 diodes connected in the ring format, and we have an input transformer 1 and output transformer 2, and the center tap of both will be used to send the carrier signal as input. There are 2 cases in operation of the ring modulator. The first case is when no modulating signal and only carrier signal is present. In such a case, all 4 diodes conduct depending upon the polarity of the carrier. In positive half cycle of the carrier, diodes D1 and D2 are forward biased and D3 and D4 are reverse biased. So no output is induced in the secondary transformer and thus the carrier will be suppressed. In negative half cycle of the carrier, it will be the opposite. D1 and D2 are reverse bias and D3 and D4 will be in forward bias. So current is divided equally in the upper and lower portions. So no output and carrier. So there will be no output and carrier is effectively balanced out. As we can see here, the carrier will be balanced out if in case 1. In case 2, both carrier and modulating signals will be present. During the positive half cycle, D1 and D2 will conduct and D3 and D4 will not conduct. So they will be in the we can say that D1 and D2 will be in the on position and D3 and D4 will be in the off position. During this time, the message signal is multiplied by 1. During the negative half cycle, it will be the reverse. D3 and D4 will conduct and D1 and D2 will not conduct. So the message signal will be multiplied by -1. When polarity of the modulating signal changes, 180-degree phase reversal takes place. So we will get the output voltage as Vm sin omega mt, Vc sin omega Ct. We can see here in this diagram the representation of case 2. And finally, coherent detection and or also known as synchronous detection. Detection is nothing but demodulation, which is the reverse process of modulation. It is a process in which original modulating signal is recovered from the modulated signal. That is, the message signal is retrieved from the modulated signal. We will be getting S of t, M of t from S of t. Coherent detection is a method to recover the message signal from a DSB-SC. In order to do that, we will be multiplying the modulated signal with a locally generated carrier. A coherent detection system will consist of a product modulator and LPF. LPF is a low pass filter. The output of the product modulator is applied to the LPF in order to allow the modulating signal, that is in order to filter the message signal. Here we can see the block diagram. We have a local oscillator, a product modulator, and the LPF. The local oscillator generates a local carrier, and we will be sending the modulated signal through the product modulator. Here we can see the equations. MT AC cos omega CT cos omega CT plus phi. We will be expanding this using cos A cos B formula, which is cos A plus B plus cos A minus B by 2. After that, we will be getting the equation MT AC by 2 cos phi plus MT AC by 2 cos 2 omega CT plus phi. Now, if we pass it through the low pass filter and only the message after the message signal is filtered, we will be getting the output as V naught T is equal to MT AC by 2 cos phi. The amplitude of the demodulated signal is maximum when phi is equal to 0, phi is phase, and minimum when phase is plus or minus 2, that is V naught will be equal to 0. This case where it is minimum, it is called as quadrature null effect.